relation applied to buckling, and as you can see, axial loading theory is no more valid. Okay, we cannot use that. So we are going to look at, before we're going to do that, I'll write out the general formula that is used in buckling. Okay, so it's equal to the critical stress is equal to pi squared EI over L squared A. So this is the general formula that we use for buckling. Okay, so this is the general formula that we will use for buckling. And someone is like, hey, what is this all about? Yes or no, right? How come this is the first time you have seen a formula in structure analysis where we have what? I mean, it's common to have E, Young's modulus. It's common to have I, second moment of area. It's common to have L, which is length. It's common to know that A is the cross-sectional area. What is the intriguing thing is, what is this pi squared doing down there, and how do we get the pi squared? Okay, how do we get the pi squared? Right. So in order to do this, okay, we are going to derive this formula. Okay. So now we are going to look at the deformation pattern. Okay, the deformation pattern during buckling. Okay. So now, usually buckling, our structure is very thin. Okay, usually. Okay, so now this is our structure. It's long, thin, with small cross-sectional area, and we have at the bottom is built in. Okay. And as I mentioned before, we're going to apply a load. Hey, how come it's going up? We're going to apply a load, and the load P is our axial load. Okay, and then over here at the top, over here, this is our point of origin. So basically, it's our datum. And then over here, we have our A. Our A is the cross sectional area. Okay. So when the structure deform, right? This is how the structure will look like. Okay. So I'm going to just draw based on the centroid. So I'm going to sketch now. This is a centroid along this axis over here. I'm only going to draw the green line. Okay. So upon deformation, right, I'm going to draw our original axis. So this is our over here. This axis is our y. Okay, and then we have a vertical. This axis over here is our x-axis. Okay. So this is where x is equal to 0. Okay. So when we have buckling, right, our deformation look like this. So I'm going to sketch out our deformation now. Okay. So this is our deformation pattern. Okay. And over here, x is equal to 0. Over down here, x is approximately equal to L naught. And L naught is this distance over here. If I will. So L naught, this distance from here. Okay. And I highlight this is approximately equal to L naught. Okay. So now, at the top over here, I'm going to call this our boundary condition number 1. When x is equal to 0, y is also equal to 0. And then over here is our boundary condition number 2. When x is equal to L naught, y is also equal to 0. Okay. So what you see over here, by looking at the deformation pattern, okay, is basically the mathematical description on how the material is deforming. Okay. Now, question for you: have you seen a deformation pattern like this before? Let's don't look at axial loading. Okay. Can anyone tell me, have you seen a deformation pattern similar to what you see that I've drawn in red and highlight in yellow? Okay. Have you seen this deformation pattern before, where you have a deformation looking like this? Anyone? You can type, you can answer me. Anyone, please.
It seems like shear deformation.
There is a bit of shear, and what else? When there's a shear, usually when there's a shear, it's also followed by what? Bending, yes or no? So if now, okay, so this is where it gets interesting. If now, okay, if now we have a structure, vertically structure like this also, right? And the structure we pin in this direction, and we have a roller on this direction, right? And then now, if we were to have a load P, right, put in this direction, what will happen? We have a deformation pattern, right? We have a deformation pattern exactly the same as buckling. Yes or no? Right? This is due to deformation pattern due to bending moment. Okay, there is a deformation due to bending moment, right? So the deformation pattern is the same. Okay, it is similar. Okay, later on we are going to we're going to apply the bending moment equations. Okay, which I will draw shortly. Now, if we were to pick, okay, if we so all of you agree that the deformation pattern is the same. Yes, all of us agree that the deformation pattern is the same. So buckling deformation pattern and bending deformation pattern is very similar. Yes, you can see that it's similar. Okay, so now let's see anyone have any question. No. So now, if we pick an arbitrary point, okay, and an arbitrary point I pick over here, and this arbitrary point is our point Q. Point Q has two very unique feature. Okay, so one of it is it has a known value of x. Okay, so it has a known value or specific distance of x, and because it's buckling, it also have a very specific distance in y. Okay, it also has a very specific distance in y. Okay, so now we are going to consider point Q. Okay, we are going to consider point Q now. Okay, we are going to consider point Q. If I were to draw, okay, so we are only going to draw to point Q. Okay, so this is our deformation. I'll try to sketch similar. So this is our deformation. Okay, until point Q. If I were to draw the forces, we know that we have a force over here, right? I'll change the color. I do apologize. Oi. Okay, so we're going to consider point Q. I need some space. Now, we know at the original point 0, 0, we have a load down here, right? And this load is our P, right? And with static analysis, right? Action equal to reaction, okay? We have a P acting down here, okay? And sketching the centroid or instantaneous axis, okay? Sketching the centroid or instantaneous axis, we know that we have a specific distance over here, right? This distance is our y. Okay. When we take, so consider Q. Okay, consider, I will change this statement. Consider at point Q. Okay, let's consider that we are at point Q. Okay, let's consider that we are at point Q. Okay, so if we look at point Q, we have a force P over here, and we have a what? A distance y. Okay, so what we have is a what? It's a moment. Okay, so we are going to have a counter moment acting this way now. Okay, we are going to have a counter moment acting this way. So this is our what? This is our moment at Q, point Q. This is equal to minus Py because it's going in the clockwise direction. Okay, let me elaborate. Okay, so now we look at point Q now, like color in red. P multiplied by y will induce a moment going this way. Yes or no? So MQ or moment at point Q has to have a counter moment which is equal to what? Minus Py. Okay, because of Newton's third law. Action equal to reaction, same in magnitude, different in what? Direction. Okay. So now if we were to write down, okay, if we were to write down, I will take this diagram. I will copy. Will come down here. Okay, by focusing on this diagram now, right? So we know that the moment at point Q is equal to what? Minus Py. Okay, that's a counter moment. So the next thing we're going to apply, we're going to do, and I think